So I'm very pleased to be at Utah State. I'm sure I know more members of the faculty here than at any university in the country, so I feel I'm among friends. I'm particularly excited to have been invited by students, which I take as evidence that my ideas are not as old and worn out as the rest of you. I'm also, yeah, okay, all right, yeah. Oh, and I've got to put this on too. But this is just for the video, right? Okay. Let's see. So how's that? Does that work? Okay. And Nancy, let me know if I'm being quiet again. Okay. So let's see. What was I saying? I think it's true that most people would rather undergo a root canal than see a lecture on statistical modeling. So I'm also really pleased to see such a full house. Thanks for coming. This was an interesting assignment that I got for tonight, to talk about something that's of broad interest that might extend beyond a particular research project. And so I gave this quite a lot of thought. And I thought perhaps the most broadly interesting thing I could talk about is something that I've learned over the last decade or so that I think would be useful to you, that you could take away and apply to your own work in a way that would increase your satisfaction with your science and perhaps would allow you to take on problems that would otherwise be inaccessible to you. So that's the plan for tonight. So what I'm going to talk about is easily the most intellectually satisfying material I have learned in a long career. And here is why it's so important. When I review papers and proposals, and particularly when I review proposals, I look for two things. There have to be some novel, exciting ideas that engage my interest. So that's the first thing. But the second thing is there needs to be what I call a line of inference that extends from those engaging ideas to new insight that's qualified by uncertainty. And the way we make that connection in science is by expressing ideas about how nature works in deterministic models, in developing a system for observations, for testing the predictions of our deterministic models, and combining that observation system and those deterministic models with probability models to get the uncertainties right. This process is so fundamental to what we get up in the morning and go do as scientists that it's truly that middle ground we must own. We must understand that deeply and thoroughly if we're to be as effective as we possibly can be in doing our research. I often hear it said that someone or another is an ecological modeler, as if the rest of us were something else. But to the extent that models play such an important part in developing strong lines of inference, a key idea in this talk is that we are all ecological modelers. So how did I get interested in Bayesian inference? Dave Schimmel and Jennifer Hoding and I organized a workshop sponsored by NSF in 2004. The purpose of the workshop was to develop a special feature for ecological applications, encouraging ecologists to expand their statistical toolkit. And the idea was that if we embrace a broader range of approaches to analysis of ecological data, then ecologists will be willing to take on a broader range of problems. That was the idea at the meeting. And Ken Newman gave a talk at that meeting. I think he called it Hidden Process Models in Ecology, but basically it was just about Bayesian hierarchical models. And he made a very simple, compelling case about how usually what we need to do is we need to model a process of obtaining observations separately from a process of modeling the ecological processes of interest. So the observation system needs to be modeled separately from the process that we seek to understand. This was a really compelling idea, and he showed in this talk how it is that we can combine in the same coherent framework monitoring data with detailed experimental studies. I was really hooked, and I started to work on those methods in 2004. Apparently, I wasn't alone, because the use of Bayesian methods has increased rapidly since about that time. So there apparently were other people who were compelled by these ideas. This is the number of papers using Bayesian methods published in Ecology since 2000. And the thing I find interesting about this slide is the fact that this cuts across all of the subdisciplines. There are no holdouts. And so the question for my talk today is this just a passing fad? Is this just something that's going to be popular for a while and then disappear? Or does this represent an enduring way, an enduring change in the way that ecologists develop lines of inference? So here's the structure of my remarks. I'll spend one slide talking in a very pithy way about what sets Bayes apart, what makes it different from the methods that you may be using now. And many of you may be using Bayesian methods, I don't know. But I'll talk a little bit about what's different about Bayes. And then, just because it's so interesting, and because it says something about the kinds of problems that can be solved using this analysis, I'll go into a history, just briefly, of Bayesian methods. And then I'll get to the meat of the talk, 6 reasons, no equations, for why Bayesian analysis is particularly appropriate for the problems that ecologists confront in our research. I'll briefly talk about a specific example from my research, modeling brucellosis in the Yellowstone bison population, to illustrate some of these advantages. And then, if time remains, I'll talk about some tips for self-teaching this material. So what is it that sets Bayes apart? Bayesians divide the world into 2 sets, things that can be observed and things that are not observed. And we learn about the observed quantities as random variables, which means we seek to understand the probability distribution from which those unobserved quantities are drawn. Classical probability theory allows us to make statements about the observations conditional on knowing the causes that gave rise to the observation. That's classical. Bayesian turns this around, and it's why it's also been called the theory of inverse probability. We are entitled to make statements about the probability of causes conditional on knowing observations. So those 2 things, treating all unknowns, all unobserved quantities as random variables, and being able to make statements about the probability of cause conditional on observations in hand, is what it is that sets Bayes apart from other branches of statistics. So just a bit of history. On the left, you may recognize, or you may not, the Reverend Thomas Bayes, who Bayesian analysis is obviously named after him. He was interested in proving the existence of God using scientific methods. And he came up with a qualitative phrasing for how we can update our current beliefs with new information to obtain revised beliefs. There was actually no math in his procedure. He laid out in a qualitative way this algorithm. To his left, in the center there, is Laplace, who the famous French mathematician Laplace, who really did the heavy lifting with Bayes' theorem. And for all rights and purposes, really we should be talking about Bayes-Laplace and not Bayes alone, because he developed the mathematical theory, and he had a more practical application in mind, the aiming of Napoleon's artillery, which is probably why he got those medals. But so Laplace was interested in the theory of inverse probability early in his career, but then became a frequentist later, largely in response to these incredibly detailed records that were kept about all kinds of phenomena in Napoleonic France. The theory of inverse probability, the idea of Bayes, was really dropped by all serious mathematicians shortly after Laplace's death. And so there really was not a field of statistics then. The mathematicians abandoned it, but it was kept alive by people who wanted to solve problems, by practitioners, in both biology and medicine, in finance, and as we shall see, in cryptography. So now we'll fast forward to when statistics really did develop as a discipline, the 1920s through the 1940s. On the far left is R.A. Fisher, who along with Newman and Pearson developed the whole idea of frequentist methods. Now, it's important to think about what's the metaphor for the development of frequentist methods. Well, it was largely agronomy. And a lot of the terminology that we use now in modern statistics comes from those roots. Split plots, randomized complete blocks, they all date back to the idea of experiments conducted in plowed fields where things were highly uniform. And the idea that we could repeat an experiment many, many times was perfectly appropriate in agronomy. I mean, these are plowed fields. We could do the same thing over and over. On the far right is Harold Jeffreys, who was a geophysicist, and he was interested in understanding earthquakes. How do you repeat an earthquake under identical conditions? It's easy to see why these two really strong thinkers had such different ideas about how we should go about making inference using observations and models. And I would argue that there are many phenomena, not all, but many phenomena in ecology that are more like earthquakes than they are like plowed fields. So the movie being all the rage, I thought I should include this. This is Alan Turing, who is responsible really for the modern digital computer. What's the movie called? The Imitation Game. So the computer gets all the credit in the imitation game, but we all know that a computer is only as good as the algorithm that it implements, correct? Guess what the algorithm was for breaking the Enigma code? It was Bayes' theorem. And so I think we can say that this is the only instance of the application of probability theory that changed the course of human history. All right, the end of history comes with Alan Gelfand and Adrian Smith, who in 1990 published a paper that I think has now been cited almost 4,000 times. The paper, up until this point, Bayesian analysis could only be applied to fairly simple problems. And I won't go into detail on this, but the numerator of Bayes' theorem has a fairly complicated integral in it if you have multiple unknowns. And if there are multiple unknowns, that simply could not be integrated. Well, Gelfand in 1990, this was new to the statisticians in 1990, came up with a way to obviate the need for integration by sampling directly from the marginal posterior distribution. This, although it was always theoretically possible, always in theory, you could use Bayes' theorem to solve very complicated problems. It was never possible in practice until Gelfand and Smith published their paper. And this is when the statisticians really started to get excited about Bayes' theorem. Okay, so 6 reasons. First of all, you can understand it. So I don't know if you recognize this. Nancy or Richard are definitely of the age that you might. This is the front piece of Sokal and Rolfe. It is a taxonomic key to analysis. So if your data are like X, then you do analysis Y, and your data are like W, then you do analysis Z. This dates back really to R.A. Fisher's statistical methods for research workers. At some point, the statisticians decided, we're going to teach the agronomists, we're going to teach the biologists methods. We're going to save math stat for the statistics majors. And so training, I think you're all nodding your heads, has usually been procedural. And we may have almost no gut level understanding of why we use analysis Z over analysis Y as a result of this kind of training. It has not served us well. I have taught my ecological modeling class since 2002. I think Peter Adler was in that first class, and Andrew Trednick was in a later one, and I take full credit for their meteoric success. But in all of those classes and in several workshops I've taught in Europe and in North America, I do the same exercise. I hand out a 3x5 card. You don't have to put your name on it, but on one side you've got to put down the definition of a p-value, and on the other side you need to write down the definition of a frequentist confidence interval. The running score right now is 15% correct answers. The answers are usually wrong, they're usually badly wrong, and they're diversely badly wrong. And so this points to me that we are not training our students to have a deep, intuitive understanding of how to develop a line of inference. And this is a real shortcoming, I think, in the way we conduct training of ecological researchers. Bayes, on the other hand, extends from 3 rules of probability. The law of conditioning and independence, the law of total probability, and factoring joint probabilities. If you know those things, you know the basis for hierarchical Bayes. Those are not difficult to understand. In order to use this theorem effectively, you do need to know some distribution theory. So basically some elementary mathematical statistics. You need a toolbox of probability distributions. And it probably behooves you, so as to not get yourself into trouble, to understand the basis of the algorithms that are used for the numerical integration. So Markov chain Monte Carlo or one of its LIs. But if you master these things, then you will be able to start with the first principles definition of probability and move step by step to the insight that you gain from your analysis, understanding every step of the way. This is the main reason. This is the most compelling reason to learn these approaches. So the second reason is that one approach applies to many, many different problems. It really doesn't matter if you're conducting a manipulative experiment on biological diversity, if you're analyzing a time series of nitrogen emissions, if you are interested in a mark recapture study of butterflies, or if you're doing a meta-analysis of invasibility, the same approach is used in all of these cases. All of the unknowns are treated in the same way, whether they are parameters in models, latent unobserved states, missing data, or forecasts. They are all treated in an identical way. And usually, we construct a model that has this sort of a structure to it. We have observations that arise from, as Ken Newman called it, a hidden process, a process that we can't see, that depends on unobserved states. So a classic example is we're interested in the true size of a population, but we rarely can perfectly observe that true size. So there are all these data models, distance sampling, mark recapture, and so on, that allow us to relate the true state Z, the size of the population, to what we're able to observe. We then have a model of the ecological process that's entirely separate from the way that we model the data. And both of those models have attendant uncertainties. The models of parameters reflect what we knew about these processes before we conducted our investigation, and that can include we didn't know very much. There are a variety of problems that are at best challenging and at worst impossible to deal with using conventional statistical approaches that can be handled deftly with the Bayesian approach. These include data that are obtained at multiple scales. A very frequent problem in ecology. We have perhaps macro plots observations within those plots and observations on the plots themselves. They extend across a regional extent. Those kinds of problems are easily dealt with. Errors in the observations of responses, errors in the observations of covariates, forecasting, understanding individual variation arising from genetics, history, or location. These are all tough problems statistically and can all be handled really quite easily in the Bayesian framework. The third reason is that Bayes can deal with problems of high dimension, with problems that are complex. And I want to explain why I think this is so important. 20 years ago, the cultural norm for analysis in ecology was the manipulative experiment, the agronomic style experiment. And when I served on panels 20 years ago, really it was very difficult to get anything past a panel if you didn't do your research this way. And this illustrates the truth of the statement of C.S. Holling that you are more likely to get your paper rejected or your proposal turned down for doing the thing wrong than for doing the wrong thing. You know, there's some real wisdom in that analysis can constrain the questions that we're really willing to ask. So don't get me wrong, this is a very important tool in ecology. I'm not saying we should abandon the designed experiment. It's the only route to being positive, to being certain about causality. It is an important tool. But if analysis of variance is the only tool that we've got in our locker, then the entire world must be composed of plots. So the strength of these experiments is also their greatest weakness. What we do when we do designed and manipulative experiments is to reduce the number of influences, isolating one or two or a small number. And yet, my goodness, we wouldn't have gotten into ecology if we didn't believe it was interesting, because there are many interacting parts, composite forces, multiple variables that influence the processes that we're interested in. And so this argues for an approach that can handle problems of high dimension. So hierarchical Bayesian models can handle analyses that have got multiple parameters, multiple sources of data, multiple kinds of data, both monitoring and experimental, latent variables, multiple sources of uncertainty arising from different causes. These sorts of high-dimensional problems would bring likelihood or frequentist methods to their knees. This is really the only route for dealing currently with these kinds of problems. So this is one of my favorites. This approach very easily supports inference on derived quantities. So what do I mean by this? Very frequently, the inference that we desire is not about what we measure and estimate, but is some nonlinear function of the quantities that we observe and estimate. So here's a great example. We might go out and do a mark recapture study, and we might estimate a fertility or fecundity of individuals and survival, stick that into a projection matrix. We've measured survival, and we can make inference on survival, but really what we're interested in is making inference on the population growth rate, as indicated by the dominant eigenvalue of the projection matrix, and the stable age stage distribution as indicated by the dominant eigenvector. How do we make inference on these derived quantities? And there are any number of other examples. We might measure who eats whom in a food web and be really most interested in some assessment of interaction strength. This is really quite easy to do, not so much because of Bayes itself, but because of the equivariance property of the MC-MC algorithm. It's trivially easy to do. I had to put this one in. I don't think it's well appreciated that Bayesian analysis supports a very well-developed framework for multi-model inference. Ecologists, and particularly wildlife ecologists, may have come to believe, as a result of the popularity of Burnham and Anderson, that the problem of model selection has been solved. And, you know, frankly, the statisticians view it very much as an unresolved problem. There are any number of approaches for selecting among models and making inference based on multiple models, and they all have strengths and weaknesses. And on our recent monograph, Mevin Houghton and I tried to outline in a very objective way, you know, what are the pluses and minuses of all the alternatives that are out there. But we can say one thing for sure, and that is, if you desire to make a statement about the probability of a model conditional on the data, you really only have one alternative, and that's the Bayesian probability of the model. There is no other route out there, despite what you might read in Burnham and Anderson, that has strong theoretical statistical grounding. So I left the best for last, I guess. So it's evaluating alternatives for management. And I think this is a really compelling reason to learn these methods, particularly for those of us at land-grant schools where this is really an important part of our mission. Informing management decisions has been important to me really since I started my career 25 or 30 years ago. So what's the fundamental problem that we confront? In all management, whether we're managing wildlife or stock portfolios, what we really need to consider is what actions do we take today? What are the actions that we take today that will enable us to meet goals for the future? That is the essential problem of management. And in ecology, you know, that could be we want to reach some goal for maintaining ecosystem services, or for sustaining the harvest of a forest, or recovering an endangered species. And we've got a suite of alternative actions, which, by the way, should include doing nothing as our null model, and we need to choose among those actions based on science. Science should have something to say about which alternative is best, and it should have something to say that is ruthlessly honest about uncertainty. So here's a general framework for doing that in the Bayesian paradigm. So what I'm illustrating here is Bayesian forecasting. This is a schematic of a state space model. And basically what state space models do is they separate the observation process from the ecological process. And so what have we got here? On the y-axis, we've got some state of a system. This could be something like the size of a population, the extent to which a community is invaded by an exotic, rates of nitrogen turnover. It could be anything. It's some state that we are interested in. And on the x-axis, we've got time. And so the little dots represent observations. And it's best that we have replicates at those spots. We never escape the need for good design, but to keep this graphic clean, I only put one up there. So the solid lines are what we call the posterior distributions of the latent state. So they're our estimate of the true value of the ecological state at each point in time. And they reflect our uncertainty about those values at different points in time. So what are the dotted lines are what we call predictive process distributions. And those are our forecasts of how the system will behave into the future. This is exactly the way that the weather is forecast, which may not impress you. However, this is also exactly the way that Nate Silver predicted 99 out of 100 states correctly in the last two presidential elections, using an approach that's exactly like this. So those distributions expand as we go out in time, as they should, because we're basing them on increasingly uncertain information. So now what I'm going to do is I'm going to take one of those dashed lines and I'm going to bring it down and I'm going to turn it on its side so it looks more familiar to you and is easier for me to illustrate the kinds of things that I want to talk about next. But we've got probability density on the y-axis, and we've got some future state of the system at some future point in time on the x-axis. So this is a true forecast. It's a prediction of future behavior that includes an honest assessment of uncertainty. So what are managers interested in? They're interested in maintaining a system relative to some goal. So the goal might be to reduce the state below a target, as we might want to do if we were going to reduce the prevalence of a disease, for example. It might be to increase the state above a threshold, which we might do if we were wanting to recover an endangered species. Or the classical problem in sustainable harvest, we want to maintain the state of the system within boundaries. So those are indicated here, and the area that's shaded represents the probability that we would meet that goal at some point in the future. So I said we should always evaluate our actions relative to a null model. I mean, basically, if we're asking what should we get up in the morning and go do, one of the alternatives should be stay in bed. So what I've shown here is the null model of doing nothing. And given that there's uncertainty in our forecasts, there's always going to be some probability, even in the no action alternative, there'll be some finite probability that we could meet our goal. And what we want to assess is the ability of some action under a forecast to increase that probability of meeting the goal. So if we forecast the effect of an action, presumably that's going to move the predictive distribution in the direction of our objective. So what we've done here by taking some management action is increase that area shown here in the hash marked lines. So we increase the probability that our goal will be met. And the net effect of management is the ratio or the difference in those two areas. So we can talk about what's the probability that the goal will be met and what's the increase in the probability that the goal will be met relative to no action given some management alternative. So what I want to do now is talk just briefly. This is not going to be a research seminar. I want to talk just briefly about some modeling of brucellosis in the Yellowstone bison that I've done to illustrate some of these several advantages of Bayesian analysis. So the first I'm going to highlight is the application of Bayes in adaptive management. That's something you may not be aware of. I'll talk about combining process studies, detailed, highly designed research projects and their results, combining those with large-scale, long-time monitoring data in the same statistical framework. I'll talk about estimating parameters in a model of high dimension. This is a pretty complex model. I'll illustrate inference on derived quantities, and then I'll show an illustration of this evaluation of alternatives for management that I just showed the general approach, but I'll show a specific approach here. So brucellosis in Yellowstone, why are we interested in it? I once gave this talk, went zipping through the slides, and afterwards somebody said to me, what's brucellosis? So let me start out by saying what's brucellosis. It's a gram-negative bacterium. It affects ruminants, in this case particularly bison, elk in Yellowstone, and the livestock in the areas that surround Yellowstone. So it doesn't affect animal survival, but it does affect reproduction, because immediately after infection, almost all infected animals abort. Then they have lower reproductive output for the rest of their lives. It's a big deal to the ranching industry, because if you lose your brucellosis-free status in a state, in Wyoming or Montana, for example, if you can't be certified brucellosis-free, you can't export your product. This is a big source of conflict. So let's talk a little bit now about Yellowstone and bison. They, of course, are an icon of conservation. At the turn of the century, the bison were almost extinct in North America, and their restoration can be attributed to the fact that there were populations of native bison in Yellowstone that could serve as sources for transplants throughout North America. And of course, now the bison are abundant throughout the United States and Canada. But just as this illustrates the success of conservation, it also illustrates the fundamental challenge of conserving a migratory species that comes into conflict with people who live outside of conservation areas. The bison migrate in response to accumulating snow. They leave the park boundaries, moving the way they traditionally always have to lower elevation, and that brings them into conflict with the park's neighbors. So this is a big problem in policy and management for Yellowstone National Park. Everybody here, I suppose, at a school like Utah State is at least somewhat familiar with adaptive management. But how many of you have read Walter's book? I mean, it's certainly been a lot written from Walter's book, but how many of you have read the source? That's what I suspected. Bayesian models occupy a central place in adaptive management as it was originally formulated by Carl Walters. It didn't bother him at the time that these were almost computationally impossible to implement. They were still a good idea. So the idea is that we develop a model of the system, we forecast the system behavior under different policy options, we implement one or better several policy options, we observe the system of the behavior, we update the model, and multiple cycles through multiple repetitions of this cycle improve our ability to manage and improve our understanding of the system. So Mevin Houghton and I have been working with the staff at Yellowstone for the past 6 or 7 years on developing a Bayesian forecasting model to support their program of adaptive management. And basically what we're trying to do is to bring together long-term data sets, annually replicated counts, aerial classification of juveniles and adults, ground classification into multiple age and sex classes, brucellosis serology, and the number of animals removed. These were the time series that we had to work with. And we also had a very detailed process study, a mark recapture study, which we used to estimate, to provide prior information on several important parameters in the model, the recruitment rate of each of the disease states, the probability that a recovered animal will become infectious again, and the probability of vertical transmission. We then withheld information on probability of infection for model selection using out-of-sample validation. So here's the model. You'll be delighted to know I'm not going to linger on this slide, but I do want to say that this is a fairly standard matrix population model used widely in population ecology to represent dynamics of organisms. There are 8 states here with different disease states and different sex and age classes. There are 9 parameters, and we're estimating those states over 41 periods. So this is a fairly highly dimensional model. And this is the full Bayesian expression for the model. It is a compact expression of the posterior distribution being proportional to what we call the joint conditional distribution. There is no excuse for not including an expression like this in your Bayesian paper. It says everything you need to know about how the analysis was done, what the inferences are that are being made. And so it provides a very compact, clear way to communicate the nature, the specifics of your analysis. So I said I would talk about inference on a derived quantity, a really important quantity in epidemiology and modeling infectious disease is what's called the basic reproductive ratio of the disease. It's the number of new infections that are created by a single infected individual in a wholly susceptible population. And the reason it's important is that if by management you can drive this quantity less than 1, then the disease will fade out. As long as it stays greater than 1, then the disease will expand or reach some sort of endemic equilibrium. It's a fairly difficult quantity to estimate using a projection matrix, a stage structure model like this. It involves matrix multiplication, a matrix inversion, and then eigenanalysis. And so based on the quantities we measure, we want to make inference on a fairly, on a quantity that is related in a highly nonlinear way to our observations. This is the posterior distribution of the basic reproductive ratio of brucellosis. We're the first to come up with that estimate. We're one of the few estimates of the basic reproductive ratio that even includes any uncertainty. So the last illustration is what we did to evaluate management actions relative to goals. The thing that Yellowstone was really most interested in was several different objectives for the bison population and evaluating several different actions and their ability to meet those objectives. So there's a lot of combinations here. I'm not going to go into all of them. But basically what we set out to do is to improve the conversation between stakeholders and managers about which of these actions are really worth taking. And what I'm going to illustrate is vaccination. So this is one of those comparisons of a no-action alternative with the vaccinate alternative. And so the dark curve is what we would expect for the goal of reducing seroprevalence to below 40%. That was one of the goals they wanted to reach. It's about 60% right now, 60% positive. And they wanted to reduce seroprevalence below 40%. Well, overall, if we take that action, there's only about a 6% chance that that objective would be met in 6 years. But there's the chance that we would meet it is twice as great as if we did nothing at all. Now, whether or not it's worth doing is a topic for conversation that involves values and involves, well, is 5 years too soon? Should we pursue this longer? I will say that the conversation in Yellowstone resulted in we're not going to do a park-wide vaccination program, simply because the probability of meeting our goals, and this doesn't include any uncertainty in your ability to implement management, the probability drops even lower if you include that uncertainty. So I started out with the idea that fundamental to science is the ability to develop compelling lines of inference. And for me, in my entire career, this body of material has given me greater confidence and greater satisfaction with this process than really just about anything else I've learned. So I recommend it to you. And if you're interested, this can be self-taught. Particularly if you're willing to teach yourself to a level where you're a good collaborator for a statistician. There are lots of books out there on how to do this. There's been a small cottage industry in ecology in cranking out books on Bayesian modeling. But there's one book that I particularly recommend that's forthcoming this July. Mevin and I have tried to take a different approach than the other texts that are available. What we've tried to do is to lay out the basic, fundamental statistical principles that you've got to have to understand this material and to be a good colleague of a statistician, to be able to write down a model properly, to be able to understand how you gain insight from that model. So this is forthcoming. We think it's going to make a contribution. I recommend it to you. There are also a couple of workshops that are available. For the elders in the room, that is postdocs and faculty, there's a workshop that Mevin and Maria Uriarte and Kiona Ogle and I teach every May. Let's see, this is our 4th year teaching it. We have support for 1 more year. I don't know whether we're going to ask to renew this or not. It's a 2-week course. It's aimed at busy people who want an accelerator for their learning. We aim this at people who are not likely to be able to take formal coursework. They're already engaged in practicing ecology as a faculty member or an agency researcher or a postdoc. And so we teach these to 20, sometimes as many as 25 practicing ecologists every May. NSF offers a $1,000 stipend to offset the cost of travel. They're interested in, they're supporting this because they want to improve the quality of the review community. And so that's why this is being supported. And then starting this August, there are going to be workshops that I will teach with a social scientist at SSYNC, the National Socio-Environmental Synthesis Center. About half of these courses will be social scientists, about half will be environmental scientists. And the motivation for this course is that, frankly, the social scientists have been using this material for a lot longer than the ecologists have. It's a shared language. You often hear it said that there's the reason that there's not progress with social science and ecologists working together is because they speak a very different language. This is the same language. The problems may differ, but the language is the same. So we felt this would be a good way to bring ecologists and social scientists together in a natural framework for synthesis. I've probably already made the case well enough that Bayesian inference is a natural for synthesis because it allows us to update current knowledge with new information. And with that, I'll take some questions or hear comments or whatever you'd like. Yes?
So you said what roles of decision makers informing them and communicating the results of your work. So do you find it easier or harder to communicate results that with uncertainty on them? So instead of just giving them numbers, you're actually giving them a range or like a number with a confidence level. Do they find that harder to understand that information?
The answer is that if I had shown them a plot of the effect of vaccination with no confidence interval, it would have been completely misleading. If I'd showed it with a confidence interval, it would have been equally confusing. This approach, I've had really good success in communicating to managers. I mean, you don't need to go into the nitty-gritty about where these distributions come from. But basically, what I outlined for you is basically the way I describe this to managers. And they get the idea of that there's this probability that's under the curve and so on. I've used this for helping decide on culling objectives for elk in Rocky Mountain National Park, for using fertility control to control white-tailed deer on the eastern seaboard in the US, for harvesting lynx in Sweden, for assessing the effect of changes in salmon fishery on the viability of killer whales in the Pacific Northwest, and this brucellosis example. And in all of these cases, I've been doing modeling for a long time, and this has been appreciated more by the policymakers, decision makers I've worked with than any approach I've tried in the past. Yes?
Devil's advocate here. So you say about 15% of people usually know what a confidence interval is. So 15%.
15.
Right. How many people would know what credible interval was?
Actually, that's the most frequent definition of a confidence interval. So the most frequent, I mean, they're diversely wrong, but to the extent that there is a common answer, it is that a 95% confidence interval is an interval such that we can be 95% sure that the true value of the parameter falls in that interval. That's what they say. That's what they want a confidence interval to be. And of course, you recognize that as a Bayesian credible interval, an equal-tailed interval. So if anything, there are a bunch of closet Bayesians in these courses. Yes?
So Tom, you started out by saying that Bayes invented this to try and prove the existence of God.
Yeah.
You've been working on this, you've written the book.
Hey! I'm more interested in aiming artillery. All that material came from this very engaging book whose author I'm going to forget. She's a historian of science. Can anybody help me with the author of The Theory That Wouldn't Die? You can get it by the title. It's a great book, not an equation in it. It's all about the history of Bayes from the 1700s through all of its applications up to the present day. And the sort of take-home message that I got that I thought was meaningful was that it was kept alive by people who wanted to solve problems across fields, finding submarines, cracking the stock market, problems in epidemiology. It was practitioners who really kept it alive. The statisticians were pretty much dismissive of it until Gelfand's paper, when they saw, you know, this is pretty handy. This can really be used to solve problems that we have not been able to solve before. So it's a great read. I really enjoyed it. And you know, to tell you the truth, it doesn't appear that Bayes' result got a lot of publicity because
Did Robert Bayes draw inference?
Yeah. I mean, that's what he was trying. That's what he was trying to establish. What? I don't know the answer to that. I would say apparently not. Incidentally, I mean, so why was a Presbyterian minister interested in all this stuff? This was fascinating too. So there were a lot of amateur scientists in England at the time, and the reason was that the only people who could be at universities were Anglicans. So if you weren't an Anglican, you didn't get to serve on any of the faculties. And so there was this group of amateur scientists that landowners, wealthy merchants, ministers, and that group of amateur scientists is what we now call the Royal Society. Yeah.
Are there any examples of just starting out with the same data,
Yeah.
a subset of data for any kind of ecological phenomenon
Yes.
process, and looking at both approaches?
Yes.
And then looking at the different conclusions or inferences that are drawn, and
Yeah.
examples of them being disparate or similar?
Right. Okay, so the general rule on that, so we really need to talk about three disciplines in statistics. Really comparing frequentist methods and hypothesis testing and p-values with Bayes is sort of like comparing apples and bookshelves. They are so different that the comparison doesn't hold. But what about comparing maximum likelihood with Bayes? Well, if you use similar priors, and priors fit just fine, thank you, in the maximum likelihood framework. It was advocated originally in the seminal text of Edwards. They're not used widely, but they can be. If you use similar priors, or if you use maximum likelihood without priors and vague priors in the Bayesian framework, for relatively simple analyses, you'll get identical answers, or almost identical. So I had this experience in the paper I'll talk about tomorrow, Kristen Marshall's paper on her experiment in Yellowstone. It went to the proceedings of the Royal Society, and Schmitz was one of the reviewers, and he said, hey, look, this is a general audience here. I know the ecologists are gaga about Bayesian methods, but this is for a broad audience, and it's an experiment. So why don't you use methods to analyze the data that are familiar to the readership of this journal? So we had a Bayesian analysis originally. There were some good reasons for doing it, but we revised it to a completely likelihood-based approach, and honestly, there was not a nickel's worth of difference in the results. Now, this will not be true for all problems. Hierarchical models that take complex joint distributions and break them down into a series of univariate distributions, that's pretty hard to do in maximum likelihood. In fact, the only way to do it has been published by Brian Dennis and Subhash Lele, these sort of violently anti-Bayesians. But even they need to trick likelihood in order to get these answers out for. They need to overwhelm the prior by cloning data. So that's fine. That's a reasonable approach. But there's really no comparison, in my view, between the models that are most powerful in Bayes, there's not an equivalent in maximum likelihood, unless you trick the model with data cloning.
For a student just coming into grad school,
Yeah.
we would traditionally recommend that they take a little course in the
Yeah, I know.
non-parametric stats multivariate.
Right.
To you, how would you envision changing the curriculum to be able to have the tool set to do this?
Well, it's a problem of getting from here to there. In the long term, I would teach students math stat, a 2-semester sequence in math stat, and then some sort of a sequence in Bayesian modeling. That's what I would do, and basically that's what most of my students do. And so we now have my class. We have a 2-semester sequence. I teach the first semester. Mevin teaches the second semester. And so I try to go over all of the probability theory and all of the distribution theory that they need, and they wouldn't need to take math stat. Basically, my feeling is that once they have that, they can invent the analyses that they need. They don't need to go to a book and look it up. They can figure it out from first principles. Any regression, virtually any analysis of variance, they can figure that out because they know how to write down the model from first principles. They certainly do need to know both approaches. But if you have a principled approach, you can read any paper that lays out an analysis of variance and understand what's going on. Frankly, I think the principled approach is far, far more efficient for students. And the example I'll give is mark recapture. I don't know if you're familiar with that, but I'm sorry, I don't know who you are. You may be a real expert, I don't know. But if you've seen the Mark book, despite its title of A Gentle Introduction, the last time I looked, it was about this thick. And in order to know where does my analysis fit in here, you need to know pretty much the whole thing. And so in order to know which of these many possibilities is appropriate for me, you need to know what the possibilities are. On the other hand, if you understand from first principles how a multinomial distribution works, you can invent the analysis that you need from those first principles for any mark recapture design. That's a lot more efficient. Now, I might say, it would be wise for you to have a good statistical colleague that once you've written this analysis out, you can go and say, what do you think about this, Mevin or Jennifer or whoever it is? But they'll be glad to have you coming in their office, equipped as you are, to speak with them as you do. So that's a really long-winded answer to a difficult question. I think the future is in a principled approach to training. But in the meantime, students need to know. They need to know what an analysis of variance is. And so, I'm a bit on the fence about this, but I've certainly had plenty of students who've been very successful, who never had a methods course.
So can you, I'm not sure if this is a question that you can answer this in a short time, but can you talk a little bit about, you keep saying like the violently anti-Bayesian.
Oh, yeah.
Can you say what is it that they are so
Yeah.
against?
Okay, so they're mainly concerned about the role of the prior. And it is true that there is no such thing as an uninformative prior. And that really concerns them. And so they're concerned that there's a degree of subjectivity that enters into the analysis via your choice of priors. And they're right. They're right. That is a problem. The way I think about it, however, and there are some other things that are more technical, that priors are not, what did they say? They are not invariant to transformation. And so You know, if you transform the prior, if you have a prior on a standard deviation and you're interested in, that's a technical topic that I won't go into, but priors are the main problem. And my feeling about that is they certainly have a point. I try to avoid the term uninformative prior, almost never using it. I may slip up every now and then, and I'll say flat prior or vague, because they're right. There's no such thing as one that's uninformative. But as long as you do a careful job of collecting lots of data, which we should do anyway, the prior doesn't make any difference. The data overwhelms the prior, particularly if the prior is flat or vague. And so that just doesn't, I don't lay awake at night worrying about that. And then the other thing is a statement by Andrew Gelman, who's a Bayesian, mostly works in social science at Columbia. And I love this statement of his. He says, flat priors are provisional. Sure, we have to start out there. But if we're really doing our job, then we're building the posteriors that we estimate become the priors in future studies. So if we're really doing our job in science, we're creating information that other people can use as priors to inform their analysis. And I think Mevin and I may be the first to really come out and pound on the table and say ecologists should use informative priors. There's really no excuse other than what is it that we know nothing about? I mean, so very often we choose vague priors because we don't want to do the hard work of scholarship to come up with a reasonable, informative one. So I guess that's the biggest shortcoming. I'm sure Brian Dennis would have other things to say. You know, he's a very effective opponent of Bayesian methods. He and Lele had a paper in that forum on hierarchical modeling that I was the associate editor for, and you know, they had Faustian bargain in the title of their paper. You know, I tried to get them to tone that down a little bit. You know, some people might be offended by that, but they stuck by their title.
Okay, I think unfortunately we're out of time, but tomorrow's talk is at 4 p.m. in the same room here, and I left the directions for the social in the back, so you can get that on your way out if you need it. But once again, thank you.
Thank you.